which are then assembled into massive fuel assemblies. The metal inside these tubes holds a fundamental secret of nature that physicists unraveled less than a century ago. It concerns a specific isotope, uranium-235. The fact is, uranium doesn't burn, it doesn't need oxygen to release heat, and it doesn't leave behind the usual ash. Instead of chemical combustion, it does something much more elegant and grand. It splits its own nucleus. To understand the mechanics of this process, imagine a classic pool table. The heavy, particle-packed nucleus of uranium-235 is like a tightly packed pyramid of balls right in the center of the table. Now imagine that another solitary ball, a free neutron, crashes into this pyramid. From the impact, the nucleus becomes critically unstable and literally splits into two parts. It is in this fleeting instant that the greatest miracle of nuclear energy occurs. When the nucleus splits, a colossal amount of kinetic energy is released. The resulting fragments fly off at incredible speeds, collide with neighboring atoms in the lattice, and cause them to vibrate wildly. In the language of the macroscopic world, this subatomic vibration means only one thing: extreme, intense heating. This is precisely the heat we need to turn water into steam. But the most interesting part happens next. When a uranium nucleus splits, 2 or 3 more free neutrons are ejected from it. They fly on and strike neighboring uranium nuclei with the same precision. Those nuclei also split, releasing another burst of heat and emitting 6 more neutrons. Then the number grows to 12, 24, 48. This is called a nuclear chain reaction. The process of neutron multiplication grows exponentially in a matter of millionths of a second. Inside the metal tubes, right beneath the water's surface, a subatomic storm of incredible density rages. And this is where the most intriguing engineering question arises. If this reaction accelerates at such a staggering rate, why doesn't the reactor melt down within the very first seconds of operation? How did engineers manage to rein in this invisible chaos and make it run like clockwork, smoothly, predictably, and absolutely safely for decades? The answer lies in precision, physical control. To tame the nuclear storm, engineers use sophisticated physics. Inside the reactor, control rods made of boron or cadmium are positioned between the fuel assemblies. These act as the system's brakes,